Okay, in this video we're going to look in a little bit more detail how to read an oscilloscope, how to make measurements about the waveforms, and some of the things that you can do with them. Okay, fundamentally what a oscilloscope is it's a voltmeter. It measures voltage, but it does so in real time. So it tells you what the voltage of a signal is at any given instant in time. And it displays that information out on a screen. And that lets us make three very fundamental measurements. Now, there are other things that you can do with oscilloscopes. Modern oscilloscopes have a lot of different functions to them, but uh, at their heart, these are the three main measurements that you make with an oscilloscope. The first one is amplitude. The second one is time, and the third one is frequency. And so we're going to look at each of those three measurements in turn. And we're going to start by measuring the amplitude, and that's the simplest. Now, there are two different ways that people typically measure amplitudes. One way is they measure it as what's called peak-to-peak amplitude. And the amplitude is just the height of the waveform. So here is one peak down at the bottom, here is a peak at the top, and so the peak-to-peak amplitude would be the amplitude, the height difference from the bottom of the waveform to the top of the waveform. And so if we look at the grid, we can see that the grid is divided into big squares, which are subdivided into little squares. And there are 1, 2, 3, 4 little tick marks in between the squares. And each of these tick marks represents 0.2. So this would be 0, 0.2, 0.4, 0.6, 0.8, 1.0. So that would be one complete division. Now, the same thing works vertically. I have 0.2, 0.4, 0.6, 0.8, 1.0. This would be one complete division. The big box represents the main divisions. And so on your oscilloscope, you can control how many volts each of those big boxes measures. And so each box, the height of each box might represent 5 volts or 2 volts or 1 volt or a millivolt or whatever it is that you dial in. So let's take a typical example that we've set our oscilloscope to measure 5 volts per division, and that's again going to be on the vertical axis. And so we simply want to determine what is the voltage of this signal. So we can say first, let's measure the peak to peak. And so the bottom is right on this line here, and the top is on that line. So the distance would be 1 division plus 1 division, 2 complete divisions. Now we know that there are 5 volts per every division, so the peak-to-peak amplitude of that signal would be 10 volts. And so we could say VPP, that stands for peak-to-peak, would be 10 volts. And that would be the peak-to-peak amplitude of that signal. Very simple to do. Now usually when we talk about amplitude, we're not talking about the peak-to-peak amplitude, but just the regular amplitude. And that's always measured from the zero. The wave is oscillating around some zero value, and the height of the wave is measured from that zero. And so from here to here would represent 1 square, and so that would be 5 volts per square times 1 square gives me a height of 5 volts. And so the regular amplitude, just the normal voltage that you would measure, would be 5 volts. And that would be the peak amplitude. The peak amplitude is 5 volts. The peak-to-peak amplitude would be 10 volts. And measuring amplitudes is really that simple. You just get the height from the center up, or you can do the peak-to-peak amplitude. Now, sometimes it's actually easier to measure the peak-to-peak amplitude, and then the relationship is pretty obvious. You're just going to divide that one by 2, because the height below and the height above should be the same. Now the next thing that we want to be able to measure is the time, and time is measured on the horizontal axis. And so again, each of these squares, if I go horizontally on the square, that represents, so if I start here at 0, that would be 0.2, 0.4, 0.6, 0.8, 1.0, 2.0, 3.0, etc. And so I want to measure the time that it takes for the waveform to repeat itself. In other words, from horizontal peaks to horizontal peaks. So if I start here and I go until I get to the next peak, that is a distance of 1, 2, 3, 4 boxes. And so that represents 4 horizontal divisions. Now we know that there are 1 millisecond in time per division. That's the time per division. So if there's 4 divisions and there are 4 milliseconds, if there's 1 millisecond per division, that means that there's a 4 millisecond difference in time from that peak to that peak. Now the time from peak to peak horizontally is called the period of the wave. And so here the period of the wave would simply be 4 milliseconds. And again, that period is the amount of time it takes for one complete cycle of the wave to execute. The third main measurement that we make with an oscilloscope, and we generally will make it indirectly, is the measurement of the frequency of the waveform. Now we just measured the time or the period of the waveform, and we found that the period was equal to 4 milliseconds, and that's 4 times 10 to the minus 3 seconds. Now there's a relationship mathematically between the period and the frequency. And if we want to measure the frequency, that's just the reciprocal of the period, 1 over the time for one complete cycle. So the period tells you the amount of time it takes for one complete cycle of the wave to complete. The frequency tells you the number of complete cycles that will execute in 1 second. So you can either talk about the time for one cycle or the number of cycles per second. And that is the measurement of frequency. And by the way, the units of frequency are 1 over seconds, which is also known as a hertz, generally abbreviated with an Hz. But the frequency is simply 1 over the period, and the period is the time between successive intervals. So what would be the frequency of this sine wave? We would simply say that the frequency would be 1 over 4 times 10 to the minus 3 seconds, and that would work out to be 250 seconds to the minus 1 power, or 250 hertz. And that would be the frequency of this sine wave. So let's look at another waveform. Let's say that this is the wave that we're looking at, and we want to know what's the amplitude, what is the period of the waveform, and what is the frequency of the waveform. Well, you can see that this waveform is not symmetric about the zero. This does not line up with any of the big boxes. So it's a little tricky to measure this, but we could do it. We could say, okay, there's the bottom, and I can go over there, and that seems to be about halfway in between that division and that division. And I could pick up here, and I could go, but that's really, there's going to be some error there. It's going to be tricky. One of the things that you can do to reduce the error in a measurement like this is to use those vertical and horizontal offset controls to scoot the waveform around on the page, just to make it easier to read these distances. So if you adjust the vertical offset and the horizontal offset, you might end up something that looks a little bit nicer. So here you can see that I have adjusted the horizontal and the vertical offsets of that waveform. Now up in the previous slide you can see that the height was up here, this was not touching the bottom, so I basically scooted the waveform down until it was touching. Now it's not always going to line up perfectly, but you could set the bottom here, for example. If the wave was a little higher, it might come up to this tick mark, but that would still be much easier to read than if it was, not sort of leveled at this bottom line here. And so by moving it left to right, moving it up and down, you can position it to make it easier to have a reference on that grid with which you can use to make your measurements. Now you can see there's no waveform right here, which looks a little bit weird. The reason for that is because I have offset it vertically to the left so that the center of this waveform lines up with one of these vertical lines. So that lets me measure the period more easily. By setting the bottom here, I can measure the amplitude more easily, and it's actually now pretty straightforward to do. So let's do that really quickly. The first thing we want to do is measure the amplitude. We still have the same setting on the oscilloscope, 5 volts for every box, 5 volts per division. And so I count up here from the bottom, there, there. Again, there's 2 volts per division. If I go from the center up, that's going to be just 1 division or 5 volts, and that's going to be the peak amplitude. So the amplitude that you're going to get is simply going to be V equals to 5 volts. And that would be the amplitude of that waveform. To get the period of the waveform, again, we want to go from one peak to another peak. And so I can see here there's going to be 1, 2 boxes here. So we go from peak to peak, and that will give me 2 divisions. We know that there's 1 millisecond for every division, so the period of that waveform is going to be 2 milliseconds. So the period is going to be equal to 2 milliseconds, or 2 times 10 to the minus 3 seconds. Now here's a trick. If you have multiple cycles visible on the screen, it actually can be better to go across those multiple cycles. So say from here to here, there is 1, 2, 3, 4 divisions over 2 periods. And so I could get a little bit more precision in my measurement by looking at a bigger distance. Because remember, the error in a measurement like this is typically going to be something like half the smallest division, half of one of these little tick marks here. Now, if I consider the error from here to there, from the one peak to the next peak, then I'm going to have that distance of half a tick mark is a pretty big segment of that. But if instead, if I consider the error from there across the whole screen, that half of a tick mark is a much less error over the whole distance. And so the relative uncertainty of that measurement is lower. So that's actually a better way to do it. But for our purposes, we're going to just, keep it simple, stupid. I'm a big fan of that philosophy. So we're just going to measure from here to here. And that's what we did. We got 2 milliseconds. If I measured 1, 2, 3, 4 divisions and 1 millisecond per division, that would say that that's 4 milliseconds from there across all of the peaks that are visible on the screen. And then we would divide that by 2 periods, because it's a period to here and a period to there. We would still end up with 2 milliseconds. Now, if the lines don't line up exactly on these vertical lines, if the signal rather doesn't line up on these exactly on these vertical lines, then giving you more waveforms is actually the better way to do it, because as I said, it reduces that error. But we have now the voltage and the period. The last thing we want to measure is the frequency. And actually, not so much measure, but calculate that, because we know that the frequency is simply 1 over the period, and that's going to be 1 divided by 2 times 10 to the minus 3 seconds, and that works out to be 500 hertz. And so the frequency of that signal would be 500 cycles per second, or simply 500 hertz. So we saw previously that a function generator can put out more than just sine and cosine functions, and one of the examples that you were shown was the square wave. And so this is a square wave. We have a constant voltage that goes, say, there to there, and then it flips up, and then you have a constant voltage again, and then it's negative, it drops down to a negative, but again, it's constant voltage here. So it's just an alternating series of constant voltages, positive and negative. And in this kind of function, there's a symmetry here. So the height is the same here. So if this is a particular voltage, this would be negative, that particular voltage. And so what is the voltage and frequency, say, of this particular waveform? Well, the voltage is relatively simple to measure. We know that if I go from the center up, I can simply count divisions. So I've got one tick mark, a second tick mark, and then it's at about a half. And we can see the symmetry here, so it's the same down below. It's 2.5 tick marks to the bottom signal, it's 2.5 tick marks to the top signal. So that would mean that the amplitude going from the center up is 2.5 divisions, or rather 2.5 tick marks. Now, we know that that would be about half a division. In fact, not about, that would be half a division. So the amount of amplitude would be 1/2 a division, and we know there's 5 volts per division, so the actual amplitude would be 5 volts per division times 1/2 division. The divisions cancel, and we're left with 2.5 volts, and that would be equal to the voltage of that signal. And of course, the peak-to-peak voltage would be 5 volts. You would just double that. Now, for getting the frequency of the signal, that turns out to be a little bit more tricky. And in order to do that, requires a mathematical technique that's a little bit beyond the scope of this material. It involves something called Fourier analysis, where basically you have multiple sine waves, each with different frequencies that you have to add together in order to get this entire signal. So rather than having a single frequency like a sine wave, this waveform would have many, many frequencies. In fact, infinitely many frequencies. It's an infinite series that you have to add up. So the bottom line is, for something like this, you generally wouldn't measure a single frequency, but the voltage is easily measured, as you saw.